Jai Hind to all. My name is Dhanshri Parihar, Assistant Professor, Department of Computer Science and Engineering, Ajay Kumar Garg Engineering College. And my today's topic is multiplication algorithm from the subject Computer Organization and Architecture. So the overview of my presentation includes computer arithmetic, representing positive and negative numbers, binary multiplication, and the Booth algorithm and its example. Now, before proceeding for the multiplication algorithm, we must know what are signed number and unsigned numbers. So, what are signed numbers? Signed numbers are the numbers in which we consider their sign, like +9, we have -9. Okay, this is a signed numbers. And what are unsigned numbers? The numbers which we always consider to be positive. And we don't consider any sign with that. We consider them to be a positive. Whereas in signed numbers, we will consider the sign of the number also. That will be either plus or either minus. So let us take an example. With the help of example, we will explain how we can represent our signed numbers. So signed numbers can be represented in computer system by using sign magnitude representation, by using 1's complement representation, and by using 2's complement representation. Now, for example, we have to represent a signed number +9 and -9 in a 7-bit binary formation. So, in a sign magnitude representation, we will represent +9 to be in a form of 0, 00, 1, 001. So, this is the binary number of 9, and here we include an extra bit which is known as your signed bit, which is the most significant bit. The signed bit, which is a most significant bit of our binary code, an extra bit. Now the value 0 will indicate the positive number, and the value 1 at the binary location of my most significant bit will indicate a negative number. For example, if we have to represent the -9 in a form of sign magnitude representation, so how we can write this similar code? We can write in this form. 001 001 is the code for 9, and here the most significant bit 1 will indicate the sign of this 9, that is -9. So 1 indicates the negative number in sign magnitude representation. Whereas in 1's complement and in 2's complement, what we will do, in 1's complement, we will invert these bits. The 1 will become 0, and 0 will become 1, 0 will become 1 again, 1 will become 0, 0 will become 1, and this 0 will become 1. And here, the most significant bit will remain 1. Why? Because we are representing a negative number, that is -9. So the code for -9 in 1 complement representation is 1 110 110. And for the same number -9, we can use 2's complement representation also. Now in 2's complement representation, first we have to add 1 to the 1's complement representation. That is the way we find out the 2's complement. By inverting the bit of the actual binary code and then adding a 1 to that code, we will get a 2's complement of a number. For example, here we are having a number 001001, that is for 9. And what we will do, we will invert the bits to find 1's complement. For this 1's complement, it will become 1, 1, 0, 1, 1 and 0. Now, how we get a 2's complement? By adding 1 to it. So, it will become 1, 1, 1, 0, 1, 1. So, it is the 2's complement. So we get 110 111 as the 2's complement of number 9. But we have to represent the number -9. For representing -9, we will insert 1. That is an additional bit. We can say a most significant bit to be a value to be 1. Why? Because we are representing a negative number. A negative number with binary bit 1 and positive number indicated by value 0. That is binary bit 0. So for -9, we have a 2's complement of 110 111 and the sign magnitude bit will be 1. So this is the way how we can represent your signed numbers by using sign magnitude representation, by using 1's complement and by using 2's complement representation. Now next is the binary multiplication. Now what is binary multiplication? We have two terms in this. One is your multiplicand and another is the multiplier. So the upper term is known as multiplicand and the lower term with which we are performing the multiplication is known as multiplier. For example, here we are having 23 and 19. So 23 is your multiplicand and 19 is a multiplier. And these intermediate results are known as partial products. Intermediate result of your multiplication. And after addition of these partial products, we will get the end result which is known as product, that is 437. So in this binary multiplication, we will get the binary code of 437. So for us, for humans, it's a very easy task to perform the multiplication. But in computer system, we have to use certain algorithms to perform the binary multiplications. And there are two types of multiplication algorithms. One is your array multiplier scheme and one is your Booth multiplication algorithm. So next we are going to discuss about the Booth's multiplication algorithm. Now what is a Booth multiplication algorithm? It is a multiplication algorithm which multiplies two signed binary integer values. As we discussed earlier, that we have a signed numbers and unsigned numbers. Signed numbers contains positive and negative signs within themselves, but whereas unsigned numbers, we are considering them to be positive always. So we are not considering their signs. So here is an example of a few terms which we can be used, or few examples which can be, by using that we can explain our Booth multiplication algorithm. Like we have a case. First case is of one number is a negative number and one number is a positive number, that is -7 and 3. Next example is when both the numbers are having positive signs with them. And the third example, when both the multiplier and the multiplicand is having the negative sign with them. So these three cases of signed magnitude numbers, multiplication. Three cases. So Booth algorithm is used for solving these three cases. Generally, it is used to speed up the performance of the multiplication process in our computer system. That is the advantage of using a Booth multiplication algorithm. So here are certain terms of Booth multiplication algorithm which we are going to use in the algorithm. So first is AC term, which stands for accumulator. And accumulator is used to store the partial products, we can say, and its initial value is always set to 0. The next, we are taking M, which is representing the multiplicand bits. That is, for example, if we are having -7 into 3, so here this will be showing our M, that is multiplicand, and 3 will be showing our multiplier. So we are representing this multiplicand with M and our multiplier with q in this example, where minus m represent the 2's complement of m. M, that is your multiplicand, and the q represents the multiplier bits, whereas q naught represent the last bit of the multiplier q. So if we are having 5 bit of code or any 4 bit of code of your multiplier, then the least significant bit will indicating your q naught value, whereas q minus 1 is a value with which we will compare our least significant bit of a multiplier, and it will be initially set to always 0. Now next is sequence counter, SC. Now sequence counter is used to keep the sequence of the iteration which we are going to do in our algorithm. Means the number of the steps which are used for solving that particular multiplication operation. So that will be defined by our sequence counter. And when the value of sequence counter will become 1, 0, then our multiplication algorithm will stop. Now let us take a look at the flowchart of our Booth multiplication algorithm, how it's going to be work, and what are the various conditions which can be fulfilled to attain our result. So this is the flowchart of Booth multiplication algorithm, which explains the step-by-step process of solving our problem and getting our result for a multiplication operation. So here, first of all, we will initialize certain term where A is a cumulator, M stands for the multiplicand. For example, in the previous example, I will be taking 7 as your multiplicand and 3 as a multiplier. So this will be your M. Multiplier, that is your 3, representing by Q. And then the count. Count means the number of steps we are going to perform for solving a problem. That will be N. And here, N will be equals to the number of bits Q or M is having. Means the size of multiplicand and the multiplier. For example, if the size of multiplicand is 5 bit and the size of multiplier is also 5 bit, then the value of N will become 5. Means the size of multiplier and the multiplicand. Next, after initializing these things, we will move to the decision. Now what we have to check the condition, whether our Q naught and Q minus 1 values will be 1, 0, 0, 1, 1, 1 or 0, 0. Now what is this Q naught and what is this Q minus 1? As we have stated here, Q minus 1 will be equals to 0. Initially we are setting. And what will be the Q? That will be the multiplier. For example, here we'll take a binary code of 3, that is 0, 0, 1, 1. So 0, 0, 1, 1 is a multiplier, that is Q will be holding this value. And here this bit will be termed as Q naught, Q1, Q2 and Q3. That is the least significant bit of that Q. This Q naught. And we have to perform the comparison between this Q naught bit and this initial 0 bit Q minus 1 over this in this flowchart here. And their value may be, we have 4 possibilities, 1, 0, 0, 1, 1, 1 and 0, 0. If the first case is the possibility of 1, 0, that is the value of Q naught is 1 and the value of Q minus 1 is 0, then what we have to do next? We have to perform this operation. That is, we have to subtract the content of accumulator with our multiplicand. And for the second case, if we have a 0, 1 value, then we have to add the content of accumulator with the multiplicand. And after performing these two operations, if that condition is true accordingly, the next step is to perform the arithmetic right shift operation. Now what is arithmetic right shift operation? In this operation, what we will do, for example, arithmetic shift right operation. For example, suppose we are having these 4 bits, that is 0, 0 and 1, 1 in a register. Now in arithmetic shift right operation, we have to shift the bits towards the right hand side. And how we are going to shift it? Now this one is removed from the register, and what we will get here? We will get this one. Next, at the location of this one, what we will get? This 0. And next, at location of this 0, what we will get? The previous 0. So we will left with one empty block over here. So what we will get in this empty block? Again, this particular bit is copied here. So in arithmetic shift right operation, what we will do? We'll shift the binary bits towards the rightmost direction by discarding the first bit and then adding the last bit to the next column as well as to it will retain its own position. So that is a arithmetic right shift operation. So after performing this arithmetic right shift operation, we will decrement the counter. Now why we are decrementing the counter? Because one step is now completed. Suppose the value of n is over here is 5, then the value of n will become now 4. And this condition will be checked over here whether that counter will become 0 or not. If it is not, then we will proceed again to the checking condition of the new values of q0 and q minus 1. If it is 0, then we will end the algorithm and we will get our end result of the multiplication. So if we are having the value of n equals to 5, how many iterations we are doing? We are doing 5 iterations, means this algorithm is going to complete and we will getting the result of multiplication in 5 steps. And in every step, we have to perform this check and perform these operations accordingly. Now, let us take the example for solving this Booth multiplication algorithm. So here, in this example, I am taking minus 7 and 3, where minus 7 is your multiplicand and 3 is our multiplier. So for minus 7, we have a binary code of 1001, and for 3, we have a binary code of 0011. This one and this one. As we know that the binary code for plus 7 is 0111. So how we will find the binary code for minus 7? By finding the 2's complement of this. And how we will find the 2's complement? First of all, we will invert the bits. It will become 1, it will become 0, 0, 0. And then adding 1 to it, we will get our 2's complement of this. And this is for value minus 7. So the code for minus 7 is 1001. That will be obtained by taking the 2's complement of plus 7. And this is our multiplier bit. Since we are taking it to be like this, minus 7 into plus 3. And our result will be minus 21. So what we will be observing that what we are expecting to be the result to be, that will be 21 with the negative symbol in it. That is minus 21. So this is your multiplicand m and this is our multiplier q. So initially we will take in all the values, and here we are considering SC, that is the sequence counter, to be with the value of 4, as we are taking the size of this multiplier and multiplicand to be of 4 bits. So that will be equals to your sequence counter size. That will be equals to your n, the number of iteration used to perform this particular Booth multiplication algorithm and to get the result, that is minus 21. So how we will obtain this minus 21? By performing 4 iterations, that is 0, 1, 2, 3 and then exiting from your algorithm. Now let us start with the algorithm. As we say that initially m is your multiplicand, that is 1001, that is minus 7, and AC is the accumulator, where Q is the multiplier and Qn plus or we can say q minus 1 according to our this flow chart. It is q minus 1 and we will taking it to be q. So it up to you, you will take it as n plus 1 or q minus 1. That will be your decision. But the value of this q minus 1 or q n plus 1 will always be 0. As we have discussed earlier, that accumulator will be 0 initially and the q minus 1, or we can say it to be q n plus 1 will be initially 0. So we will be putting it value to be 0. AC is also 0 and this q will be, that is your 3, as we know that this is your multiplier. So its value is 0011 and we are putting sequence counter to be 4 for this question, as we will be taking the size of multiplier and multiplicand bit to be of 4 bits. So that's why we will taking it to be 4. So this is our very first step where we are initializing our registers. That is the register A, that is accumulator, register Q minus 1, our multiplier register Q, and the multiplicand register to be M. Now, the next step. In the next step, we have to perform a comparison between the Q naught and Q minus 1 bit. That is the comparison between the least significant bit, that is between this bit and this bit. That is the least significant bit of this Q and this Q n plus 1. And here the value of this Q naught is 1 and this is 0. So what we are comparing? Q and Q minus 1, Q naught and Q minus 1, and the value is 1 and its value is 0. Now let us have a look at the flow chart. If the value is, here we value is 1 0. If the value is 1 0, what operation we have to perform? We have to perform this operation. We have to subtract the multiplicand from the accumulator contents. So here accumulator is, this is the operation we are going to perform according to that flow chart. That is the very first step after comparison, and the content of accumulator is initially 0 0. So we will putting 0 0 0 minus, and what will be the value of minus m? So here we have got one confusion over here. Every time when we used to put a minus, the value of m is minus 7. If I am saying that AC equals to AC minus m, but what will be the value of m? This value of m according to this example is minus 7. So it will become like this, AC minus 7, which will become plus 7. So what will be the code which we will be using over here? We will writing it like AC plus, or we can say this will become a plus symbol, and that is 1 0 1 1 1, and here we are having this plus symbol, not minus but plus symbol over here, and we are performing the addition between these two binary operands. And what will we get as a result of this binary addition? 0 0 0 0 is going to add with 0 1 1 1. That is a plus 7 and the contents of your accumulator. So it will become 1 1 1 and 0. Again we will be getting this as a result. That is the new content of a accumulator, and the value of accumulator is now updated from 0 0 0 to 0 1 1 1. This will be the new value of accumulator. Now moving back, when we have performed this operation and we will get the updated value of accumulator, after doing that we have to move to the next step, and next step is to perform the arithmetic right shift operation. As I told you earlier, what is the arithmetic right shift operation? In which we move the bits toward the right hand side and copying the last bit, that is the most significant bit, to the it will maintain its previous location also and move forward also. So this is the way how we perform a arithmetic right shift operation, and same we have to do with our example. So here, if I am saying this is the content of accumulator and this is your content of your we can say Q, that is 0011. So let us have a look how we'll perform this operation. Now the current content of AC, Q and Q minus 1 we can say, or we can say Qn plus 1. What will the current contents after updation? Like in AC we are having a 0 1 1 1 and Q is having this 0 0 1 1 and this is having this 0. Now what we have to perform? The arithmetic right shift operation, and in that operation we have to move them towards the right hand side. So what will we do? This 0 will get vanished, and what will we get? We will get 1 at this particular location in place of this 0. And here we will get this 1, here we will get this 0, here again 0, and in place of this 0 what will we get? This 1 will be moved over here, and this will become our new Q, and this will become our new Q minus 1. And in AC we have this 1 to be here, then again 1, then again 0. It will be copied in a forward direction also and maintain its position also. That is the arithmetic right shift operation. Now if we are having 1 over here also, then again same thing we will do with the 1 bit also, 1 binary bit. 1 will be moved further and will be copied in the previous location also. It's not only for 0 but for 1 also that we have to perform the same operations. So we will get this result after performing our arithmetic right shift operation. This complete value over here, that is 0011 1001 and then 1. So as we see earlier, we have performed this arithmetic right shift operation, and after that we have to compare the value of that count, and that should not be 0. Previously the value of count is 4, so 4 minus 1 will become 3, and here we are comparing 3, so our this value is not 0, and again we have to move to this comparison step. So we will have a sequence counter to be 3, and again we have to go to the comparison step. In comparison step, again we have to perform the comparison between the Q0 bit and the Qn plus bit, that is this bit and this bit. Now at this particular step, that at step number 3, the value of Q and Q minus 1 will become now 1 1, that is Q0 and Q minus, the least significant bit of the multiplier and the Q minus 1, it will become 1 1. And what we will do for 1 1, if the value of this Q0 and Q minus 1 is 1 1, then we do not have to perform any addition or subtraction of that accumulator, and we do not update the value of accumulator. But what we will do, we will only perform a arithmetic right shift operation. So here we directly perform a right shift operation. We will move this 1 outside, this will be vanished, discarded, and what will we get over here? This we will get this 1, and at the location of 1 we will get 0, then again 0 over here, and then we will get 1 over here. This 1 will be shifted over here, and we will get 1 0 0, and again this 0 is inserted over here, and we will get the new values of Q, A, C and our Qn plus 1. These new 3 values we will get. Now again we have to reduce this counter, that is n minus 1 it will become, so it will become now 2. Again we have this will become now 2 for iteration 2. Now it will be coming 2 after performing arithmetic right shift operation, it will become 2, and we have to again go back to the comparison over here, and we have to again compare Q0 and Q minus 1 bit that we are currently having, and we have to do this procedure again and again till we will get this count to be 0. So here we will got to the step number 2. What we will do here, we will perform again this comparison operation between the Q0 bit and this Q0 bit and the Qn plus 1 bit. Now the values will become 0 and 1 for comparison, and if the value is 0 1, what we have to do, we have to perform an addition operation, that is addition between the accumulator's current contents and the multiplicand bit. And this, in this example, the current value of AC is 00001 for step number 2. And what will be the multiplicand value? That will be -7, and that will be represented by 1001. So we will be adding this 1001 AC and your multiplicand. And what will we get? 1 is 0 and carry is 1. We will get 1 0 and again 1. So we will left with the new accumulator updated value, that is 1 0 and 1 0. This one. Now after performing this operation, we have to again perform this arithmetic right shift operation on the current value of AC, Q and Qn plus 1. Like this. And after performing that right shift operation, we will get these values and the counter will be also reduced to 1. Now again, we are not having the 0 value of the counter. We have to again perform the comparison operation. And again, we are comparing 0 and 0. Now when it will be 0 0, what we will get, we will move to directly to the step of arithmetic right shift operation. And on this particular pair of bits, we can perform this arithmetic right shift operation. And what we will get, this 0 is discarded. We will get 0 over here, and this 1 over here, this 1 over here, this 0 over here, again this 1 over here, and then so and so on. And this 1 is copied to its next location, this one, the previous one, this one, and it will move forward and copy to its previous location also. Here, that is like 1 0 1 0 1 1 0, and then we have 0, and we have to perform this, and it will be like this: 1 1 1 0 1 0 1 1, and we'll be left with this. And here we will get this answer, and this is our -21. And how we will get this minus? This is actually not the exact value of -21. We have to perform the 2's complement of this, and we will get -21. That is the result of -3 into +3 -20. Like this. Thank you.